going to discuss about equilibrium equation in Cartesian coordinate. Okay. Now, as let us assume a infinitely small parallelopiped. Parallelopiped is a shape. You can say it is a three-dimensional object of the parallelogram. Okay. So when the internal angles of the parallelogram is 90-degree, it becomes a rectangle. Okay. And when all internal angles are equal to 90-degree and all arms are of the same length, it becomes cube, or in two dimension it will become a square. Is it okay? So we just consider a infinitely small parallelopiped rectangular parallelopiped. It means all the internal angles are of 90 degrees. Uh, so let us this we have a axis. This is called z axis, and we have y axis, and we have x axis. As we have discussed earlier, that there are one direct stress at each panel and two shear stresses parallel to each panel exist. Okay, so consider this point. This is sigma x, and parallel to this plane is tau xy and tau xz, because this is the x-axis. So the direction of the direct stress will be in the direction of x. So that's why in this phase it is considered as sigma x, and in this phase this is taken the direction of sigma x. And now perpendicular to the two mutually perpendicular directions of this sigma x will be treated as tau xy and tau xz. Okay. Now tau xy is written because this is in the y direction, and same tau xy is in this direction, in positive y and in negative y, and this tau xz is in the direction of z axis. Here it is in the downward direction, here it is in the upward direction. And the reason is the simple, because of the equilibrium, to achieve the equilibrium condition. Okay. Now, just to start with this feature, and we will replicate all the stresses in the to the other planes. Okay. Now, when this is a small piece of a large body, and this is a direct stress of sigma x on this plane. Now, what will be the value of this sigma x on this plane? Because we know that these two stresses are dx distance apart. So because of the concept of stress gradient, which we have discussed earlier, the amount is increased by how much? The del sigma x upon dx, rate of change with respect to length, multiplied by the total length. This will give you the total amount which is being differed from this point to this point. Okay. So sigma x will become, after a dx distance apart, it will become the del sigma x upon del x into dx, and it is being added in the sigma x. That's why these two points are having this only change of this much. Okay. Now similarly, for this tau xy, a tau xy is written here, and how much it will be added? Del tau xy upon del x, because it is dx, x distance apart, multiplied by dx. Okay. So what it represents? Change of tau xy in the direction of x, and multiplied by the total distance by which it differs. So tau xy plus del tau xy upon del x into dx. Now the value of tau xz will become, this is tau xz, Now this will be in the opposite direction, and plus del tau xz upon del x plus dx. So this is the changed values from this panel to this panel. Now same thing will happen to every other panel, for the Z panel and for the Y panel also. After changing this change, what we need to do? We need to devise a equilibrium condition. So as it is, so what you have to do? You have to sum all the forces in one direction and equate it to a zero if there are no outside body force, or if there is a body force, then put equals to that value. See this. This is what it has been done here. Now, as you can see, the amount of just one minute. So if you want to write here the equation, see, let us take in the summation equilibrium of all the stress in the direction of x. See, first force is this value, sigma x plus del sigma x upon del x into dx. And at what area this stress is applied? Because this is a direct stress and we are talking about the equilibrium of forces. So force is the stress multiplied by the area. So this is the stress, and this stress is acting on the area, which is multiplied, which is totally is the area is dy and dz. The area of this panel is how much? Length into width. So this is dz length and this is dy length. So the area of this panel is dz dy. So the force is how much? This amount multiplied by dy and dz. Okay. And what force is negative to it in the x direction? Obviously sigma x. So minus sigma x multiplied by, again, on what area it is acting? Dy and dz. This is dy and this is dz. Okay. So this is the balancing force. See, in this part of the equation, it is written sigma x plus del sigma x upon del x into dx, and the whole is applied on dy dz minus sigma x multiplied by dy and dz. Okay, so this is one component. Now what is the second component? Second component, see, one thing you should keep in mind, when we are summing all the forces in one axis, so only consider that forces which is directed towards the x-axis. So obviously these two is perpendicular to x-axis, so this will not be considered here because their component in x direction is 0. Now we have to take this value. This is directed towards the x-axis. See, this is directed towards the x-axis parallel to this. So this force has component in x direction. Now what will happen? Tau xy plus del tau xy upon del y into dy. Whole is multiplied on which area? Dx into dz. Okay. So this stress applied on dx dz area. Okay. Minus this tau xy, this is in the direction of minus x, so minus tau xy multiplied by the area dx into dz. Now same thing you can see here, tau xy del tau xy upon del y into dy, and multiplied by on dx dz, and minus tau xy dx dz. Now again sum. Find another force which is directed towards x-axis. This is this. See this shear stress. this is directed in the aligned in the x direction. So tau xz plus del tau xz upon dz into dz. This is the stress acting on which area? Dx and dy. So multiplied by dx and dy minus this tau xz multiplied by which area? Dx and dy. You can see here tau xz dz dx into dy minus tau xz dx into dy. So you have collected all the forces which are aligned in x direction with its symbol, with its direction sign. So whatever is directed towards positive x will be treated as positive, and whatever directed toward minus x will be treated as minus. So now, one thing to make this thing is in equilibrium, it is also being assumed that B is a force component of the body force in x direction. Okay, Bx is the component of body force in x direction expressed per unit volume. So if there is a body force acting on this small body, then the value of this Bx exists, and if there is no body force exists, then you can easily make it 0. But for derivation purpose, we add a body force in the direction of x. So it will call Bx. And the body force is acted on the volume. So that's why the volume is dx, dy, dz. The volume of entire cube, dx, dy, and multiplied by dz. This whole force is equal to a value which is equal to how much? Rho dx dy dz into ax bar. And what it is? Ax bar is acceleration in x direction. Acceleration means if there is a motion, acceleration in x direction, and rho is the density of material of the paralleloid. So you all aware that this is basically representation of a inertia force. Okay, so if body is in movement, the inertia force is acting on the body, and this inertia force is basically density multiplied by volume. It means weight of mass of the material multiplied by its acceleration. So it is you can consider it as a mg kind of ma. So the popular equation is F equal to ma. So we are basically taking the equilibrium of all forces. So force is m into acceleration. So this is a mass rho into dx dy dz and acceleration m. Okay. So this is force equal to mass into acceleration. So after considering this equation in x direction, what we have? We some points are cancelled like this. See, when you open this statement, sigma x multiplied by dy dz in positive and sigma x dy dz in negative, there is exist. So these two is cancelled out. Similarly, these terms having the same out values are cancelled out. So what will be left? The left thing is del x upon del x dx multiplied by dy dz dx dy dz. Similar dx dy dz is left here, and similar dx dy dz is left here, and another bx into dx dy dz is common to all the equation point, and similar simple dx dy dz is written here. So we can cancel all the dx dy dz, and we only left with del sigma x upon del x minus, sorry, for plus del tau xy upon del y and plus del tau xz upon del z plus bx is equal to rho ax bar, which can be seen here. Okay. Similarly, for other axes of y and z axis, the thing can be written easily uh, by taking the summation of all forces in y and z direction one by one. We can reach out to the equations in y and z direction. Okay. Now, if in the absence of inertia and body forces, we get what is the equilibrium equation? If there is no body force available, then this term of body force will become zero. And if there is no inertia force or the body is in static form, so this term is also zero. That's why the equation becomes 2 equal to 0. These three equations are termed as the equilibrium equation in Cartesian coordinate. Okay, so so are you able to understand?
Yes, sir.